Hello everyone. If you are aiming to become a Databricks certified machine learning professional, you are in the right place. I have gone through the newly updated official syllabus, summarized the key topics in detail, and compiled a comprehensive study guide to help you approach this exam. Please note that this content represents my own efforts and is not affiliated with my employer. Generally, I create my own notes, so I thought why not share my notes here as well, right? So let's get started on the journey to help you become certified.
Databricks Certified Machine Learning Professional Section 1, Experimentation Data Management 1. Read and write a Delta table overview of Delta Lake in Databricks. Delta Lake is an open source storage layer that brings ACID transactions and schema enforcement to data lakes. It enables reliability and performance improvements over traditional data lake file formats. By using Delta tables, you can perform efficient updates, merges, and time travel queries, which are critical for iterative machine learning experimentation and data versioning. Using Delta tables in ML workflows. Machine learning workflows often involve iterative data exploration, feature engineering, and training. As you refine features or experiment with different modeling approaches, you need to reliably store and retrieve data versions. Delta tables allow you to reliably track changes to your datasets over time. Versioning. Query historical states of a dataset. Time travel. Support structured operations like update, merge, and delete, which are especially important for dynamically maintaining training and inference datasets. Reading and writing Delta tables. Objective. Learn how to read from and write Delta tables in Databricks. Writing data to a Delta table. Suppose you have a Spark data frame containing your processed features. To write it out as a Delta table, #assume feature underscore df single quote is a Spark data frame with your features feature underscore df dot write dot format Delta. Mode overwrite. Say v slash mount feature underscore store feature underscore table 1. Format Delta specifies that you're using the Delta format. Mode overwrite overwrites existing data. Other modes include append, ignore if exists, or ignore. Save path, the path to store the Delta table in your data lake. In production scenarios, this could be an external path, often backed by a cloud storage location. Alternatively, you can create a managed Delta table by registering it with the Metastore. If you have permissions and want a managed table, feature underscore df dot write dot format Delta. Mode overwrite. Say vstable my underscore catalog dot my underscore schema dot my underscore feature underscore table. 2. Reading data from a Delta table. Once written, you can load the Delta table as a data frame for further processing, model training, or inference. Reading a Delta table from a path df equals spark.read.format Delta. Load / mount feature underscore store atra underscore table. Reading a managed Delta table from the Metastore df equals spark.table my underscore catalog dot my underscore schema dot my underscore feature underscore table. 3. After reading, df is a Spark data frame ready for transformations, analyses, or feeding into a model training routine. 2. View Delta table history and load a previous version of a Delta table. Viewing Delta table history and time travel. Objective. Understand how to inspect table history and use time travel to revert or query previous states of the data. View Delta table history. Every time you perform write operations on a Delta table, a version history is maintained. You can inspect this history to understand what changes were made and when. Describe history, Delta / mount feature underscore store feature underscore table. 1. This command returns metadata about each commit, including user operations, timestamps, and version numbers. Time travel. Loading a previous version of a Delta table. Databricks Delta supports time travel, allowing you to query older snapshots of your data. This is crucial in ML experimentation, where you might want to train a model on a previous version of the dataset or compare results from different points in time. You can load a previous version by specifying a version number or a timestamp. # using version number old underscore df equals spark.read.format Delta. Option version s off 5. Load / mount feature underscore store feature underscore table. # using timestamp must match the format of the commit timestamps. Old underscore df equals spark.read.format Delta. Option times to pass off. August 10th, 2024 T0000. 00Z. Load / mount feature _ store feature _ table. 2. Using this feature, you can reliably reproduce experiments by training or validating your models against historical data snapshots. 3. Create, overwrite, merge, and read feature store tables in machine learning workflows. Working with the feature store, Databricks feature store is a central governance layer for managing features used in machine learning. It facilitates feature discovery, ensures consistency across training and inference, and manages feature lineage. Features stored here can be reused by multiple models, improving productivity and reducing duplication. Key operations. 1. Create a feature table. A feature table is a tabular data structure that stores features along with primary keys and potentially timestamps. For example, suppose you've engineered features for a recommendation model. From Databricks.feature _ store import feature store client fs equals feature store client # assume features _ contains columns user _ feature _ feature _ fs.create _ table name equals my _ catalog.my _ schema.user _ features primary _ keys equals user _ df equals features _ df description equals user level features for recommendation model. 2. This creates a new feature table backed by a delta table registered in the feature store. The table schema, primary keys, and descriptive metadata are stored, enabling easy retrieval and governance. Overwrite a feature table during development. You may generate updated features. Instead of appending to the existing table, you can overwrite it. fs.write _ table name equals my _ catalog.my _ schema.user _ features df equals new features df mode equals overwrite. 3. This replaces the existing data while maintaining the table definition. Overriding is useful when regenerating a stable snapshot of features for a given point in time. Merging data into a feature table. One of the most powerful delta operations is the merge capability. With merge, you can update plus insert changes into your feature tables. This is crucial for maintaining up-to-date feature sets for evolving entities, such as users, products, or sensors. For example, suppose you have new partial updates for some users. #new _data _df contains user _id and updated feature values fs.merge. Source equals new data _df. Target equals my catalog.my schema.user features. Primary keys equals user id. 4. Behind the scenes, this operation uses delta's merge command to efficiently apply updates, ensuring that the feature store always reflects the latest feature values. Reading a feature table. You can read feature tables as a data frame, just as you would with any delta table. Features equals fs.read _ table my catalog.my schema.user features. 5. This data frame can then be joined with your training labels or used directly as input to your ML model training pipeline. Integrating with machine learning workflows in ML production scenarios, you often have iterative cycles. 1. Experimentation. Generate new sets of features and write them to a delta or feature store table. Track different versions of training data and labels using delta time travel. Compare model performance when trained on different historical snapshots of your features. 2. Validation and reproducibility. By using describe history, you can pinpoint exactly which version of the data was used to train a particular model. You can reload a previous version of the data at any time, ensuring experimental reproducibility. 3. Continuous integration and delivery of features. As new data arrives, use merge to update the feature store with incremental changes. Keep the features in sync between training and scoring environments. Summary and best practices. Reading and writing delta tables. Master these operations to efficiently handle your training datasets and intermediate feature sets. Using table history and time travel, enable data reproducibility and experiment iteration by pinning models to specific data versions. Leveraging feature store operations, centralize feature management, ensure consistency between training and inference, and maintain a historical record of feature evolution. Continuous updates. Use merge to keep feature tables up to date with the latest entity data, ensuring that your models always train and predict on the most relevant information. Experiment tracking 1. Manually log parameters, models, and evaluation metrics using Milflow. Milflow Experiment Tracking Overview. Milflow is an open source platform to manage the ML lifecycle. It includes Milflow tracking, record and query experiments, runs, parameters, metrics, tags, artifacts. Milflow models, a model packaging format and tools to serve models. Milflow registry, store and manage model versions. A typical ML workflow involves running multiple experiments with varying parameters and hyperparameters. Milflow simplifies this by logging parameters, input variables for the model training process, for example, learning rate, max_depth, metrics, key performance indicators, for example, accuracy, precision, recall, artifacts, output files produced during model training, for example, model files, plots, data snapshots. Manually logging parameters, models, and evaluation metrics using Milflow parameters and metrics. Import Milflow #start to run under the default experiment or specify an experiment_id with mlflow.start_run as run. #log parameters mlflow.log_param max_depth 10 mlflow.log_param learning_rate 0.01 suppose we train a model and compute metrics accuracy equals 0.92 precision equals 0.90 log metrics mlflow.log_metric accuracy mlflow.log_metric precision 1. This code snippet starts a run, logs parameters and metrics, and ends the run automatically at the end of the with block. Logging models. Milflow supports logging different model types: Sklearn, PySpark, TensorFlow, PyTorch. For example, if using scikit-learn, from sklearn.ensemble import random forest classifier import mlflow.sklearn model equals random forest classifier max_depth equals 10 model.fit x_train y_train with mlflow.start_run mlflow.sklearn.log_model random_forest_model 2. This saves the trained model as an artifact and records metadata about the model type and dependencies. It also enables model serving and loading in subsequent runs. 2. Programmatically access and use data, metadata, and models from Milflow experiments. Programmatically accessing and using data, metadata, and models from Milflow experiments after you have runs logged. You may want to programmatically query them. Query experiments and runs. Import Milflow from mlflow.tracking import Milflow client equals Milflow client #list all experiments equals client.list_experiments for xpin experiments. Print exp.experiment_id exp.name #query runs for a specific experiment_id equals 123,456 runs equals mlflow.search_runs experiment_ids equals experiment_id print runs.head data frame of runs with params metrics tags 1. Retrieve run metadata and artifacts run_id equals runs.alloc 0 run_info equals client.get_run run_id print run_info.data.params #dictive log parameters print run_info.data.metrics #dictive logged metrics #download artifacts client.download_artifacts run_id random_forest_model /local path 2. Loading a log model_URI equals f runs /run_id /random_forest_model loaded_model equals mlflow.sklearn.load_model model_URI predictions equals loaded_model.predict x_test 3. This allows you to reproduce predictions or deploy the model elsewhere without retraining. Advanced Experiment Tracking 1. Perform Milflow experiment tracking workflows using model signatures and input examples. Milflow experiment tracking workflows with model signatures and input examples. Model signature. defines the schema of input and output data for a model. This helps ensure that future inputs match the expected model inputs. Input example, a small representative sample of the input data. It's logged along with the model to clarify how to call the model. Logging a model with signature and input example, import mlflow.python from mlflow.models.signature import infer_signature predictions equals model.predict x_test signature equals infer_signature x_test predictions # create a small input example input_example equals x_test.alloc 5 with mlflow.start_run mlflow.python.log_model artifact_path equals model python_model equals model_wrapper signature equals signature input_example equals input_example. This makes the model more portable and safer to deploy as MLflow will check input schema before scoring. 2. Identify the requirements for tracking nested runs. Requirements for tracking nested runs. Nested runs allows structuring complex workflows. For example, multiple training steps in a single parent run. Requirements must start a parent run first. mlflow.start_run. Within that run's context, start nested runs by specifying nested equals true. With mlflow.start_run run_name equals parent_run as parent #parent run logging mlflow.log_param parent_param 42 #nested run with mlflow.start_run run_name equals child_run nested equals true mlflow.log_param child_param 7 mlflow.log_metric child_accuracy 0.85 another nested run with mlflow.start_run run_name equals child_run_2 nested equals true mlflow.log_param child_param_2 3 mlflow.log_metric child_loss 0.2 nested runs are useful for hyperparameter tuning experiments or multi-stage model building processes, providing a well-structured lineage. 3. Describe the process of enabling autologging, including with the use of hyperopt enabling autologging, including with hyperopt autologging. MLflow can automatically log parameters, metrics, and sometimes models from supported frameworks such as mlflow.sclern.autolog, mlflow.pitart.autolog, mlflow.tensorflow.autolog, mlflow.spark.autolog. Autologging reduces manual logging overhead. Example, import mlflow.sclern mlflow.sclern.autolog with mlflow.start_run. Model equals random forest classifier n_estimators equals 100 model.fit x_train y_train parameters and metrics are automatically logged. Integration with hyperopt when running hyperparameter optimization. Using hyperopt on Databricks, you can configure MLflow to track each trial as a run. From hyperopt import fmin, TPE, HP, status_OK, trials import MLflow def objective, params, with mlflow.start_run nested equals true, model equals random forest classifier *** params, model.fit x_train, y_train ac equals model.score x_val, y_val mlflow.log_param params mlflow.log_metric val_accuracy ac return loss ac status_ok space equals max_depth hp.choice max_depth 5 10 15 n_estimators hp.choice n_estimators 50 100 200 mlflow.set_experiment O_experiment with mlflow.start_run run_name equals hyperopt_tuning best equals fmin fn equals objective space equals space algo equals tpe.suggest max_avals equals 10 mlflow.log_param best_params Best, each HyperOpt trial is recorded as a nested run under the main tuning run, allowing you to compare results easily. 4. Log and view artifacts like SHAP plots, custom visualizations, feature data, images, and metadata logging and viewing artifacts. SHAP plots, custom visualizations, images, metadata artifacts provide additional context about your model's performance and explainability. SHAP plots. Explainability. Suppose you generate a SHAP plot for feature importance. You can save it as a PNG file and log it. Import SHAP import matplotlib.pyplot as plt explainer equals SHAP. Tree explainer model SHAP underscore values equals explainer dot SHAP underscore values x underscore test # generate summary plot and save SHAP dot summary underscore plot SHAP underscore values x underscore test show equals false plt dot savefig SHAP underscore summary dot png # log as artifact mlflow dot log underscore artifact SHAP underscore summary dot png 1. This artifact can then be viewed in the Milflow IE within the run. Custom visualizations, feature data, images, and metadata. You can log any file as an artifact. For example, a CSV of feature data, a model architecture diagram, or a SIN metadata file. #log CSV file containing feature importances feature underscore importances underscore df.to underscore CSV feature underscore importances dot CSV index equals false mlflow.log underscore artifact feature underscore importances dot CSV #log a SIN metadata file with open metadata.sin w as f sin.dump description run metadata timestamp str datatime.now f mlflow.log underscore artifact metadata.sin 2. These artifacts are crucial for reproducibility and explainability. They help future users understand what transformations and analyses were performed during the experiment. Best practices use consistent run naming conventions and parameters to quickly identify what was changed between runs. Log model signatures and input examples to ensure that models are easy to validate and deploy. Leverage autologging for rapid experimentation, but remain aware of what gets logged automatically. For complex workflows, combine autologging with manual logging. Use nested runs to structure multi-step pipelines or hyperparameter tuning experiments. Regularly log artifacts, visualizations, configuration files, SHAP plots to provide context and support explainability. Utilize the Milflow IE and programmatic queries to track performance over time, compare models, and quickly drill down into the details of successful experiments. Section 2. Model Lifecycle Management Pre-Processing Logic 1. Describe an Milflow flavor and the benefits of using Milflow flavors. What is an Milflow flavor? Milflow flavors are a convention that Milflow uses to define a standardized format for packing ML models. Each flavor indicates how a model is stored, loaded, and served. For example, Milflow provides built-in flavors like Python function, pyfunc, a generic flavor that supports models as Python functions. Sklearn, for scikit-learn models. TensorFlow, PyTorch, SparkMlib. Each framework has its own flavor. Benefits of using Milflow flavors. 1. Interoperability. Flavors provide a consistent interface for model serving and evaluation. A model logged with one flavor can often be loaded and served in a different environment without refactoring code. 2. Portability. By adhering to a defined flavor format, models can be deployed to multiple platforms, Databricks, local servers, Docker containers, etc. 3. Ease of integration. Flavors let you plug into Milflow's model serving and model registry features effortlessly. For example, a pyfunc model can be easily deployed using Milflow's built-in serving command without needing special code. In essence, flavors standardize how models and their dependencies are tracked and stored, making it simpler to move models from training environments to production. 2. Describe the advantages of using the pyfunc Milflow flavor. Advantages of using the pyfunc Milflow flavor. Pyfunc is a generic Milflow model flavor that wraps arbitrary Python models so they can be loaded as generic mlflow.pyfunc models. Invoked uniformly via a common predict interface. Deployed easily on various platforms that support the pyfunc flavor. Key advantages. 1. Framework agnostic inference. The PyFunc model exposes a standard predict function, allowing you to load and run predictions without knowing the underlying ML framework. Whether the model is a scikit-learn model, a custom Python model, or something else, you can handle inference the same way. 2. Custom pre-processing and post-processing. PyFunc models can encapsulate not just a trained model, but also arbitrary Python code that pre-processes inputs or post-processes outputs. This lets you deploy the entire prediction pipeline as a single unit. 3. Easy deployment. PyFunc models can be served out of the box using MLflow's built-in serving tools. For example, MLflow models serve Model or integrated into other serving infrastructures. In short, PyFunc provides a flexible abstraction layer that standardizes inference and deployment steps, simplifying the operationalization of complex ML pipelines. 3. Describe the process and benefits of including pre-processing logic and context in custom model classes and objects. Including pre-processing logic and context in custom model classes. When you log a model using PyFunc, you can define a custom Python model class. This class can include pre-processing steps, data transformations, feature engineering, or normalization steps can be embedded in the model's predict method. For example, converting categorical features, scaling values, or encoding inputs before passing them to the underlying ML model. Context. MLflow passes a context object to the load_context and predict methods. This context can include model artifacts, data schema info, or environmental information. You can leverage this to dynamically select logic or resources. Benefits. 1. End-to-end pipeline in one artifact. Traditional model deployments often only serve the model's prediction logic. With custom classes, you encapsulate all necessary transformations alongside the model. This reduces the risk of training serving skew, where the model sees differently processed input data at inference time than it did at training. 2. Simplified maintenance. Pre-processing and model logic co-located in the same codebase and version together means that changes to the pipeline are tracked in sync. If you revert the model version, you revert the pre-processing logic too. 3. Reproducibility and governance. By including the entire pipeline in the model artifact, you simplify governance and reproducibility. Anyone loading the model gets the exact transformations needed for correct inference, ensuring consistent results. Model Management 1. Describe the basic purpose and user interactions with model registry. Basic purpose and interactions with the model registry. MLflow model registry is a central repository to manage model lifecycle stages, staging, production, archived, versions, and associated metadata. Key capabilities include centralized management. Store all your models in a central location. Users can find and reuse models with ease. Versioning. Every time you register a new model version, for example, after retraining, you can track it alongside previous versions. Stages and lifecycle management. Promote models from none or staging to production after they're validated. Archive old versions when they're no longer needed. User interactions. Data scientists register new models or new versions of existing models. ML engineers promote models to production or archive them. Business stakeholders and MLOps engineers can track model evolution and decide which versions to use. In short, the model registry supports a formal governance and lifecycle process for models, making them easier to track, evaluate, and deploy in production. 2. Programmatically register a new model or new model version. Programmatically registering a new model or model version. You can register models using the MLflow Python client or AI. Example using the Python API. Import MLflow from mlflow.tracking. Import MLflow client equals MLflow client. # assume you have a run_id that contains a logged model artifact model_URI equals f runs /run_id/model. # register a new model result equals mlflow.register_model model_URI equals model_URI. Name equals my_churn_prediction_model. # the above call creates a new registered model if none exists. # and a new version under that model name. Print registered model version, result.version. Subsequent training iterations can create new versions by calling mlflow.register_model with the same model name, but a new model underscore URI. 3. Add metadata to a registered model and a registered model version. Adding metadata to a registered model and a registered model version. Metadata can include descriptions, tags, or additional information to help users understand model differences. Add tags or description to the model. Client.update_registered_model name equals my_churn_prediction_model description equals this model predicts customer churn probabilities. Client.set_registered_model_tag name equals my_churn_prediction_model key equals use_case value equals churn_prediction. Add tags or description to a specific version. Client.update_model_version name equals my_churn_prediction_model version equals 1. Description equals version 1 trained on Q1 2024 data. Client.set_model_version_tag name equals my_churn_prediction_model version equals 1. Key equals data_source value equals 2024_Q1_data_lake_snapshot. This metadata helps in downstream decision making, ensuring that model consumers understand the differences and origins of each version. 4. Identify, compare, and contrast the available model stages. Identifying, comparing, and contrasting available model stages by default. MLflow Model Registry supports these stages. 1. None. The default stage when a new model version is created. It's a stageless state indicating the model is registered but not assigned a lifecycle stage. 2. Staging. A model that's undergoing testing, validation, or internal evaluation is in the staging stage. It's not yet production ready, but it's been identified as a candidate. 3. Production. A model that's ready for broad use, often integrated into production systems or customer-facing applications. Production models are generally considered stable and safe for inference at scale. 4. Archived. Older models or models that are no longer relevant get moved to the archived stage. They're retained for historical or regulatory compliance purposes but not meant to be served. Comparison. Staging versus production. Staging is for evaluation and testing. Production is for ready-to-use, stable models. Archived versus none. None is for newly registered models not yet assigned a purpose. Archived is for models that were once used or staged but are now stored away for historical reasons. 5. Transition, archive, and delete model versions. Transitioning, archiving, and deleting model versions. You can programmatically change model stages using the MLflow client. Transitioning a model version. Client.transition_model_version_stage name equals my_churn_prediction_model version equals 1. Stage equals staging, # after validation. Client.transition_model_version_stage name equals my_churn_prediction_model version equals 1. Stage equals production, archiving a model version. Client.transition_model_version_stage name equals my_churn_prediction_model version equals 1. Stage equals archived, deleting a model version or a registered model. Delete model version. Client.delete_model_version name equals my_churn_prediction_model version equals 1. Delete entire registered model. Client.delete_registered_model name equals my_churn_prediction_model. Be careful with deletes. You typically archive versions rather than delete them unless you're sure they're no longer needed. Model Lifecycle Automation 1. Identify the role of automated testing in MLCI/CD pipelines. Role of automated testing in MLCI/CD pipelines. Automated testing is critical in maintaining the integrity and reliability of the ML lifecycle, especially when multiple data scientists and engineers collaborate and frequently update code, data, or model configurations. Key points: quality assurance, automated tests, unit tests, integration tests, Model performance tests ensure that changes in data processing, feature engineering, or model architecture do not break existing functionality or degrade model performance. Continuous integration (CI). Automated tests run upon every code commit or merge request, catching issues early in the development cycle before they propagate downstream. Continuous Delivery Deployment (CD). Automated testing in pipelines ensures that only models and code-passing validation tests are deployed to staging or production, improving the reliability and trustworthiness of production models. In essence, automated testing helps maintain stability, reduces defects, and provides confidence that each step of the model lifecycle, build, train, deploy, is functioning as intended. 2. Describe how to automate the model lifecycle using Model Registry Webooks and Databricks Jobs. Automating the model lifecycle using Model Registry Webooks and Databricks Jobs. Model Registry Webooks are a feature of MLflow Model Registry that allow you to define callbacks (HTTP requests) when certain events occur, such as a new model version is registered. A model version transitions stages, for example, from staging to production. By pairing these webooks with Databricks jobs, you can trigger automated workflows. For example, 1. Model promotion event. When a model version is promoted from staging to production, a webook fires. 2. Job execution. The webook triggers a Databricks job that could run final validation notebooks, update dashboards or documentation, deploy the model to a serving endpoint or external system. This orchestration reduces manual intervention, ensuring models move through the pipeline smoothly and consistently. 3. Identify advantages of using job clusters over all-purpose clusters. Advantages of using job clusters over all-purpose clusters. Job clusters are ephemeral clusters created and terminated with each job run. Compared to all-purpose clusters, 1. Cost efficiency. Job clusters spin up when needed and shut down after the job completes, preventing resource overuse. 2. Isolation and reproducibility. Each job run gets a fresh cluster environment, reducing cross-run contamination of state or dependencies and ensuring reproducibility. 3. Security and governance. Since each job run is isolated, it's easier to maintain consistent environments and security controls, as no long-running shared state persists. All-purpose clusters are suitable for interactive development, but for CI/CD and automated model lifecycle tasks, job clusters are preferred due to their cost-effectiveness, isolation, and reproducibility. 4. Describe how to create a job that triggers when a model transitions between stages. Given a scenario, creating a job triggered by a model transition event to automate tasks upon model lifecycle events, you can use the following approach. 1. Create a webbook in the model registry. Specify the event type. For example, model_version_transitioned_stage. 2. Point the webbook to a Databricks job. Configure the webbook so that when the model transitions from, say, staging to production, it sends an HTTP post request to the endpoint that triggers a specific Databricks job. 3. Job configuration. The triggered job can run a notebook or a script to perform tasks such as validation, updating metadata, or initiating a deployment. Scenario example: when a data scientist promotes a model version to production in the model registry IE or via API, a webbook automatically starts a Databricks job that runs a notebook performing final checks and updating downstream services. 5. Describe how to connect a webbook with a job. Connecting a webbook with a job. To connect a webbook to a Databricks job. 6. Obtain the job's trigger endpoint. A. Databricks Jobs API can provide a URL or token to trigger a run. 7. Configure the webbook. A. In the model registry, create or update a webbook specifying the event trigger, for example, model_version_transitioned_stage, and set the job_spec in the webbook configuration. If using the Databricks REST API for webooks, you pass the job details as part of the webbook creation call. 8. Validation. A. Test by manually transitioning a model version and verifying that the job runs automatically. 9. Identify which code block will trigger a shown webbook. Identifying which code block will trigger a given webbook. Webooks in the model registry trigger on specific events. If you have a webbook defined for model underscore version underscore transitioned underscore stage, any code that calls client.transition underscore model underscore version underscore stage name equals me model version equals 2 stage equals production will trigger the associated webbook. The code block that causes the model stage to change is the one responsible for firing the webbook event. Another example is registering a new model version, which would trigger a webbook listening for model underscore version underscore created. 10. Identify a use case for HTTP webbooks and where the webbook URL needs to come. Use cases for HTTP webbooks and webbook URL requirements use case. Suppose you want to notify an external system like a Slack channel, a monitoring dashboard, or a CI/CD service like Jenkins whenever a model is promoted to production. You'd set up an HTTP webbook that sends a post request with model details to that external system's endpoint. Webbook URL requirements. 11. The webbook URL must be a publicly accessible endpoint or at least accessible to the Databricks environment. 12. For external integrations, this could be a secure HTTPS endpoint exposed by your company's services, a CI/CD platform endpoint, or a serverless function, for example, AWS Lambda, Azure function, configured to handle the incoming request. 13. Describe how to list all webbooks and how to delete a webbook listing and deleting webbooks. You can manage webbooks using the Milflow Model Registries API or Milflow Client Library. Listing webbooks from mlflow.tracking import Milflow client equals Milflow client webbooks equals client.list underscore webbooks for hook in webbooks. Print hook. This will print details of all existing webbooks, including their IDs, event triggers, and target URLs. Deleting a webbook. To remove a webbook, you need its ID. Client.delete underscore webbook. It equals webbook underscore it underscore to underscore delete. This permanently removes the webbook, stopping it from triggering future events. Best practices and summary 1. Use Milflow flavors, especially PyFunk, to ensure consistent and flexible model deployment. 2. Encapsulate pre-processing logic in the model artifact to maintain a reliable and versioned end-to-end pipeline. 3. Use the model registry to track model versions, lifecycle stages, and metadata for governance and reproducibility. 4. Staging and production stages help enforce a formal promotion process, ensuring only well-tested models reach production. 5. Tags, descriptions, and metadata add clarity and help teams quickly identify suitable models for their use cases. 6. Archiving and deleting ensure your model repository remains manageable and focused on currently relevant models while still maintaining historical traceability where necessary. 7. Automated testing ensures quality and reliability within MLCI/CD. 8. Model Registry Webbooks plus Databricks Jobs enables fully automated pipeline triggers on model lifecycle events. 9. Job clusters, preferred for CI/CD tasks due to their ephemeral, isolated, and cost-effective nature. 10. Job triggering on model transitions. Configure a webbook on stage transitions to run a job that validates, updates, or deploys models. 11. Connecting webbooks and jobs through model registry and jobs apiece. Link model events to job runs for continuous delivery. 12. HTTP webbooks, used for external notifications and integrations. Requires a known URL from the external system. 13. Managing webbooks. List existing webbooks and delete them if they're no longer needed. Section 3. Model Deployment Batch 1. Describe batch deployment as the appropriate use case for the vast majority of deployment use cases. Batch deployment involves periodically computing predictions for a large set of inputs and storing these predictions for downstream consumption. This is in contrast to live or online serving, where predictions are computed on demand for single inputs or small batches in real time. Why batch deployment is appropriate for most use cases. Predictive workloads are often not time-sensitive. Many business problems, such as daily sales forecasts, churn probability calculations for all customers, or product recommendations updated weekly, do not require millisecond latency predictions. Cost-effectiveness and scalability. by running inference on a large batch of data at scheduled intervals, for example, nightly or hourly. You leverage efficient cluster usage. You scale computation up when needed and shut it down after the batch run finishes, reducing overall costs. Stable pipeline integration. Batch predictions can be easily integrated into ETL/ELT workflows. For example, a nightly job that extracts data, runs predictions, and then stores results back into a data warehouse or Delta table is straightforward to manage and version. Simplicity. Batch processing reduces complexity in the overall architecture since you don't need a low-latency inference serving layer or an always-on endpoint. 2. Identify how batch deployment computes predictions and saves them somewhere for later use. How batch deployment works: computing predictions and saving them for later use. 1. Load input data. Read features from your feature store, Delta tables, or a data warehouse. 2. Load the model. Use MLflow's load_model function to load a registered model from the model registry. 3. Generate predictions. Apply the model to the entire input dataset. This might involve using a Spark data frame and a UDF user-defined function for distributed prediction. 4. Save predictions. Once you have predictions, write them into a persistent storage layer, often a Delta table, so that downstream systems or dashboards can use them later. These predictions are pre-computed and readily available. Example, high level, from mlflow.pyfunc import load_model model equals load_model models /me model production input_df equals spark.read.format delta. Load/mount data input_featurez predictions_df equals model.predict input_df to pandas # for small data or local usage # for large scale. Use a Spark UDF approach covered later. Predictions_spark_df equals spark.create a data frame predictions_df predictions_spark_df.write.format delta. Mode overwrite. Save/mount data predictions. 3. Identify live-serving benefits of querying pre-computed batch predictions. Live-serving benefits of pre-computed batch predictions. Querying pre-computed predictions for real-time use cases. Even if your primary prediction generation is in batch mode, you can still support quasi-real-time lookups. Consider low-latency access. Instead of recomputing predictions on demand, you can store them in a fast access table or key-value store. Downstream applications like web apps, buy dashboards, or recommendation engines can quickly query the pre-computed predictions. Inherent scalability. Serving becomes a matter of a simple query operation rather than model inference. This architecture scales more easily since read operations are generally less resource intensive than performing live predictions. By adopting a batch-first approach, even services that appear to need real-time predictions can often be satisfied by retrieving the most recent pre-computed batch results, reducing infrastructure complexity and cost. 4. Identify less performant data storage as a solution for other use cases. Using less performant data storage for certain use cases. Not all batch predictions need to be stored in a highly performant or costly storage layer. Sometimes, you might store them in a lower cost, less performant storage system like cheaper object storage if the use case does not require fast lookup times. Predictions are used for offline analysis, reporting, or training subsequent models. The scale of your predictions is enormous, and cost savings on storage outweigh the need for extremely quick read times. This flexibility allows you to optimize storage solutions depending on the performance and cost trade-offs. 5. Load registered models with load_model. Loading registered models with load_model. MLflow's load_model function simplifies the model retrieval process. Instead of dealing with raw model files or environment setups, you can 1. Register your model in the model registry. 2. Load a specific version or stage by referencing models/modelnum stage or models/modelnum version. You ensure that the pipeline always retrieves the correct model artifact with the right dependencies. Benefits: eliminates manual model file handling, ensures consistency and reproducibility, supports environment management and packaging through MLflow. From mlflow.py func import load underscore model equals load underscore models slash me model production # load the production model 6. Deploy a single node model in parallel using spark underscore udf. Deploying a single node model in parallel using spark underscore udf. If your model inference code is single node Python code, you can still leverage the distributed computing power of Spark by wrapping the model inference logic as a spark udf. 1. Load the model locally. Load the model on the driver node. 2. Create a UDF. Use mlflow.py func.spark underscore udf spark model underscore URI to create a Spark UDF. 3. Parallelize inference. Apply the UDF on Spark data frames columns. Spark will distribute the work across the cluster, enabling parallel inference at scale. This approach allows you to batch large inference workloads efficiently, making full use of cluster resources without rewriting your model code for distributed execution. 7. Identify Z-ordering as a solution for reducing the amount of time to read predictions from a table. Z-ordering for faster reads. Z-ordering is a data skipping technique that collocates related information in storage. When reading predictions from a delta table, what is Z-ordering? Z-ordering reorganizes the data to cluster on certain columns. For queries frequently filtered by a particular column, for example, customer underscore id or date, Z-ordering reduces input-output by enabling efficient data skipping. Benefit: for large prediction tables, Z-ordering can significantly lower the read time. Queries that focus on certain columns can skip large data chunks, improving performance and lowering compute costs. Optimize delta / mount data predictions order by customer underscore id. 8. Identify partitioning on a common column to speed up querying. Partitioning for speeding up queries. Partitioning data by a common column, for example, date, can also speed up queries. Partitioning physically separates data into different directories based on column values. A query that filters on that column can then skip entire partitions, saving both time and costs. When to partition: if your queries often filter by a single column like date, region, or product underscore category, partitioning by that column is a natural way to reduce scan times. Combining partitioning and Z-ordering can yield even better performance enhancements in certain scenarios. 9. Describe the practical benefits of using the score underscore batch operation. Practical benefits of using score underscore batch operation. The score underscore batch operation is often used in Databricks workflows to streamline batch inference. Simplicity: provides a built-in method to run batch inference, reducing boilerplate code. Integration with Feature Store: if you're using the Databricks Feature Store, score underscore batch can automatically fetch the required features and apply the model at scale. Consistency ensures that the same logic that was used during training is applied at inference time, reducing training serving skew. Benefits: accelerates model deployment since you don't have to manually write Spark inference code. Handles large-scale batch inference seamlessly. Improves productivity and reduces errors by standardizing the inference workflow. Summary of key points. 1. Batch deployment is common. Most use cases don't need immediate predictions, making batch inference more cost-effective and scalable. 2. Pre-computed predictions for live queries. Storing batch predictions allows faster, simpler real-time responses by simply reading data instead of running inference on the fly. 3. Data storage choices. Use lower-cost storage when fast performance isn't critical. 4. Model loading with load underscore model simplifies retrieving models from the registry with correct dependencies. 5. Distributed inference using Spark underscore UDF parallelizes single node inference code across a cluster for large-scale prediction. 6. Z-ordering and partitioning optimize data layout to speed up queries on large tables. 7. Score underscore batch operation provides a streamlined approach to running batch inference reliably and efficiently. Streaming 1. Describe structured streaming as a common processing tool for idle pipelines. Structured streaming as a common tool for idle pipelines. Structured streaming is a scalable and fault-tolerant stream processing engine built on the Spark SQL engine. It's widely used for continuous data ingestion and transformation, whether data is coming from Kafka, Delta tables, or cloud storage. Structured streaming allows you to process this data continuously as it arrives. Incremental idle Instead of waiting for batches of data to accumulate, you can transform data as it streams in, updating aggregates and tables in real time. Consistency and fault tolerance. With structured streaming, stateful processing, and checkpointing, you can handle restarts and failures transparently. These properties make structured streaming ideal for continuous etl processes that need near real-time updates of downstream systems. 2. Identify structured streaming as a continuous inference solution on incoming data. Structured streaming as a continuous inference solution beyond etl. Structured streaming can run inference continuously, continuous inference, as new data, for example, events, logs, transactions, arrives. A streaming job applies a model to generate predictions in real time. No need for batch windows. Rather than waiting for a batch of data, the model inference runs on data as soon as it's received, enabling low latency updates to analytics dashboards, alerting systems, or recommendation engines. 3. Describe why complex business logic must be handled in streaming deployments. Handling complex business logic in streaming deployments. Why handle complexity in streaming? Real-time decisions. Many streaming use cases involve real-time alerts, fraud detection, or dynamic pricing. Complex business logic ensures predictions aren't just generated, they're acted upon correctly. Data quality and enrichment. Streaming pipelines often need to join incoming data with reference data sets, handle late or out-of-order data, or apply intricate rules. This complexity must be encoded into the streaming logic to produce accurate, timely insights. ML inference in context. Real-time predictions may need contextual features. Complex feature engineering or logic ensures the predictions are meaningful and actionable as soon as they're produced. 4. Identify that data can arrive out of order with structured streaming. Out of order data arrival. A key challenge in streaming systems is that events may not arrive in straight chronological order. Event time versus processing time. Structured streaming allows handling based on event time when data was generated rather than ingestion time. This ensures correct computation of time-based aggregates and predictions. Watermarking introduces thresholds for how far behind event time you expect data to arrive. This helps handle late data gracefully, updating aggregates and predictions as out-of-order events come in. 5. Identify continuous predictions in time-based prediction store as a scenario for streaming deployments. Continuous predictions in time-based prediction stores scenario. Predicting store sales continuously over time and updating a predictions table every few minutes or seconds. By reading the inbound transaction data stream, continuously scoring it with a model, and writing predictions to a time-partitioned delta table, you achieve a near real-time prediction store. Downstream consumers, dashboards, alerting systems. Read from this table to get the most recent predictions without manual batch triggers. 6. Convert a batch deployment pipeline inference to a streaming deployment pipeline. Converting a batch deployment pipeline inference to streaming. Batch streaming for inference. Instead of reading a static dataset once, you define a streaming source, for example, Kafka topic or directory with new files. Apply the same transformations and inference logic continuously as data arrives. Write predictions to a streaming sink, another table or message queue. Example pseudocode, # instead of a one-time spark.read.load. Define a streaming read stream _df equals spark.readStream. Format, delta. Load /mount data streaming _input # apply inference udf to the streaming data predictions equals stream _df dot with column prediction inference _udf features # write out continuously predictions dot write a stream. Format delta. Output mode append. Option checkpoint location /mount checkpoint / start /mount data streaming _predictions 7. Convert a batch deployment pipeline writing to a streaming deployment pipeline. Real-time converting a batch deployment pipeline writing to a streaming deployment. Similarly, if your batch pipeline wrote predictions once per day to a table, a streaming pipeline can write continuously as data flows in. Use write a stream instead of write and specify output modes append, complete, update, depending on your aggregation needs. This ensures predictions are always up to date without manual triggers. 8. Describe the benefits of using real-time inference for a small number of records, or when fast prediction computations are needed. When real-time inference is beneficial. Real-time inference, also known as online serving, is appropriate when small number of records. Instead of scoring millions of rows in a batch, real-time inference focuses on single or small sets of records on demand. Immediate response needed. Use cases like fraud detection at transaction time, product recommendations on a website, or chatbots providing instant responses need predictions in milliseconds. Real-time inference is costlier because it requires a low-latency infrastructure like model serving endpoints, fast databases, or a memory data stores, but it's necessary when the business problem demands immediate results. 9. Identify JIT feature values as a need for real-time deployment. JIT, just-in-time feature values for real-time deployment. Real-time predictions often require up-to-date contextual features. For example, users' current session behavior, recent transactions. JIT feature computation, compute features on the fly rather than relying on pre-computed batch features. Reduced latency. The model serving infrastructure must quickly fetch or compute the required features before running the model's prediction. This ensures that the model's inputs reflect the current state of the world at prediction time. 10. Query a model serving enabled model in the production stage and staging stage. Querying a model serving enabled model in production and staging. When using Databricks model serving production stage, a model in the production stage is typically stable and used for live traffic. Staging stage. Models in staging can be tested for canary deployments or as /B tests before fully promoting to production. You can query the serving endpoint associated with the model stage by sending REST requests. For example, using bash curl x post https / less than workspace URL greater than / model endpoint h authorization bearer less than token greater than d data. Depending on your endpoint configuration, you can direct traffic to staging models for testing or to production models for live inference. 11. Identify how cloud-provided RESTful services and containers is the best solution for production-grade real-time deployments. Cloud-provided RESTful services and containers for production-grade real-time deployments. Real-time serving at scale often leverages containerized deployments. Run your model behind a load balancer in containers, Docker Kubernetes, provided by AWS, Azure, or GCP. RESTful piece, standard HTTP interfaces for prediction requests, making it easy to integrate with microservices or external applications. CI/CD integration, automate rollouts, /B tests, and scaling strategies. This approach is well suited for high-demand, low-latency scenarios, providing reliability, scalability, and maintainability that a pure batch or streaming solution might not achieve. Summary and best practices. 1. Structured streaming, ideal for continuous and real-time inference over incoming data streams. 2. Complex logic and streaming must handle late out-of-order data and integrate feature transformations and business logic inline. 3. Conversion from batch to streaming, straightforward by using streaming reads and writes, enabling continuous processing and predictions. 4. Real-time inference for low latency, essential when predictions must be delivered immediately and features must be computed. JIT. 5. Model serving stages, use staging for testing and production for stable deployments, and query models via REST APIs. 6. Production-grade real-time, container-based deployments in the cloud with RESTful endpoints ensure scalability, reliability, and seamless integration into enterprise architectures. Section 4. Solution and Data Monitoring Drift Types. 1. Compare and contrast label drift and feature drift. Comparing and contrasting label drift and feature drift. Feature drift occurs when the distribution of the model's input features changes over time. For example, if your model was trained on users from North America but is now receiving traffic mostly from Europe, the distribution of certain demographic features, age, region, language, may shift. Label drift occurs when the distribution of the target variable label changes. For example, a churn prediction model may face label drift if the definition of churn changes due to business rules, or if customer behavior fundamentally shifts. For example, customers churn at a different rate due to economic changes. Key difference. Feature drift affects the input distributions. You're feeding the model different types of input data than it was trained on. Label drift affects the outputs the model is supposed to predict. Even if the input data stays the same, the relationship to the label may change. 2. Identify scenarios in which feature drift and/or label drift are likely to occur. Feature drift scenarios, seasonal changes in purchasing behavior. Features like number underscore of underscore items underscore in underscore cart may have different distributions in holiday seasons. Demographic shifts. A recommender system initially trained on one region starts receiving users from another region with different preferences. Data pipeline changes that alter feature encoding or sampling. Label drift scenarios. Definition of success changes. A credit risk model trained to predict default might see changes in what is considered a default by the business. External economic conditions. Changes in market conditions may shift the frequency of churn or default events. Gradual or sudden policy changes. A healthcare model for predicting patient outcomes could see shifts if treatment protocols change. 3. Describe concept drift and its impact on model efficacy. Concept drift refers to changes in the relationship between input features and the target label. Even if the features and labels appear statistically similar, their underlying relationship can shift. For instance, if a set of features originally predictive of churn no longer predict it because consumer tastes or competitor landscapes changed, the model's efficacy declines. Impact, reduced accuracy or performance. The model may still receive similar features, but they no longer correlate with the label as before, causing performance to degrade. Need for frequent retraining. To maintain accuracy, teams often need to regularly retrain or update the model to capture the new data patterns. Drift tests and monitoring. 1. Describe summary statistic monitoring as a simple solution for numeric feature drift. A simple baseline approach for detecting numerical feature drift is to compare summary statistics, mean, median, standard deviation of your current production data to those from the training data or a known reference data set. Process. Calculate summary stats over time windows, for example, weekly. Compare changes from baseline. If the mean or variance differs significantly from historical patterns, it suggests drift. Limitation. This is easy to implement but may miss subtle changes in the distribution shape, for example, a bimodal distribution shifting modes. 2. Describe mode, unique values, and missing values as simple solutions for categorical feature drift. For categorical features, simple checks like mode has the most frequently occurring category changed or become less frequent. Count of unique categories. Are there new categories appearing or old ones disappearing? Missing values. Has the rate of missing or unknown categories changed? These simple indicators provide a first-level alert for categorical feature drift. 3. Describe tests as more robust monitoring solutions for numeric feature drift than simple summary statistics. Statistical tests can detect finer-grained distribution changes that summary statistics might miss. Examples include Kolmogorov-Smirnov (KS) test compares the cumulative distributions of two samples to detect any difference. Jensen-Shannon divergence (JSD), a symmetric measure of difference between two probability distributions that's more robust than just comparing means or variances. Using these statistical tests provides more sensitive and reliable detection of subtle distribution shifts in numeric features. 4. Describe tests as more robust monitoring solutions for categorical feature drift than simple summary statistics. Simple statistics like mode or count of unique values might not capture the full distributional change. Statistical tests tailored for categorical distributions. Chi-square test checks whether the frequency distribution of categories has changed significantly. For instance, if certain categories appear more frequently while others decline, a chi-square test can quantify the significance of this shift. 5. Compare and contrast Jensen-Shannon divergence and Kolmogorov-Smirnov tests for numerical drift detection. Comparing divergence and statistical tests for drift detection. Jensen-Shannon divergence (JSD) and Kolmogorov-Smirnov (KS) test are common tools to detect numeric feature drift. Jensen-Shannon divergence measures the similarity between two probability distributions, always between 0 and 1, with 0 indicating identical distributions and higher values indicating greater divergence. Works well for comparing discrete probability distributions. less sensitive to outliers, and provides a nicely bounded metric. Kolmogorov-Smirnov KS test, a non-parametric test that compares cumulative distribution functions of two samples. Detects differences in location, shape, and scale of distributions. Sensitive to any type of difference in distribution shape, which makes it a strong general-purpose test. Comparison. JSD gives a sense of how different two distributions are on a scale. The KS test provides a hypothesis test framework with p-values to indicate whether differences are statistically significant. Often both are useful. JSD for a continuous monitoring metric, KS for a formal statistical test. 6. Identify a scenario in which a chi-square test would be useful. Identifying a scenario for chi-square test. The chi-square test is great for categorical data. A common scenario, a recommendation system predicts product categories of interest. During training, categories are uniformly distributed, but in production, you start seeing a shift. For example, electronics suddenly become much more dominant than clothing. A chi-square test can confirm whether this shift in the distribution of categorical outcomes or features is statistically significant. Comprehensive drift solutions 1. Describe a common workflow for measuring concept drift and feature drift. A typical workflow involves 1. Baseline and ongoing data collection, store training distributions, and regularly sample production data. 2. Initial simple checks. Use summary statistics and simple categorical checks for quick detection of large shifts. 3. Advanced statistical tests. If simple checks show anomalies, run KS tests, JSD measurements, or chi-square tests for a more accurate assessment. 4. Concept drift indicators. Monitor performance metrics, accuracy, precision, recall on recent data. If these degrade while the input distribution remains stable, it suggests concept drift rather than just feature drift. 5. Alerts and notifications. If a test indicates significant drift, trigger alerts to data scientists or MLOps teams to investigate. 2. Identify when retraining and deploying an updated model is a probable solution to drift. If you confirm significant, persistent feature drift that invalidates your model's assumptions. Label or concept drift that reduces model performance on recent data. Then retraining the model on more recent data or developing a new model is often necessary. Updating the model pipeline ensures the model stays aligned with the current data landscape. 3. Test whether the updated model performs better on the more recent data after retraining. 1. Validation on new data. Split recent data into validation sets and compare performance metrics of the old and new models. 2. A/B testing in production. Gradually roll out the updated model to a portion of traffic and compare predictive accuracy, user engagement, or business KPIs against the old model. 3. Statistical significance. Use statistical tests to confirm that the performance improvements are not due to chance. If the updated model consistently outperforms the old model, fully deploy the new model. Summary and best practices. Distinguish drift types. Understand whether feature drift, label drift, or concept drift is occurring, as solutions vary. Use hierarchical checks. Start with simple summary statistics and progress to more robust statistical tests if anomalies are detected. Use appropriate tests, JSD and KS for numeric features, chi-square for categorical features. Continuous monitoring. Integrate drift detection into continuous monitoring pipelines to catch issues early. Responding to drift. When drift is confirmed and affects performance, retraining or updating the model is a common remediation. Validate improvements before fully deploying the new model.
If you found this guide helpful, please share it. And don't hesitate to let me know if you would like to see more content like this for other certifications. I have no plans for monetizing this channel, even in the future. I do it simply to help others. But hearing your feedback genuinely motivates me to keep going. Good luck on your journey to become a certified professional. Thank you.